Z-scores is probability stuff, is what my day starts off with. So why is a Z-score? What is a Z-score? Well, a Z-score is what we call a standardized score. Standardized score. They just used, spelled wrong. They just use the Z as a indicator of a variable, so they use an X or anything else. They use the Z is what somebody deemed it a long time ago to have it represent a standardized score in statistics. Why do we standardize? My typical example of why do we do this is we like to compare data. We like to compare one thing to another thing. And so, would it be fair to compare males and females, their heights? Well, typically when you think about heights with males and females, who's typically taller? Males. So when I'm looking at data, males are typically taller, so it really would not be fair to compare the two genders for height. We'd rather just stay within that gender and compare the data. Like when you guys grew up and you went to the doctor's office, and they would measure your weight and they measure your height, and they'll tell your parents, hey, listen, your child is in this percentile. Well, that means they was actually use the Z. They use the Z scores because the Z scores represents a percentile. What percent of the data is to the left of it? And so they would say, hey, you're in the 35th percentile for height, which means that 35% of the kids your age and in your gender are smaller than you. That also means 65% of them are taller than you. Okay, but that's where you guys may not know it, but that's what your parents as adults when we take our kids to the doctor's office. That's when we use percentiles. We use percentiles with test skills or scores all the time when you think about the ACT or any standardized test. That, hey, I'm in this percentile for mathematics, I'm in this percentile for English. And so that's where we see it a lot. In less than 1 month, today is March the 4th, in less than 1 month you guys take the ACT. Okay, for real. All right, first half of the day on that April the 1st, it's not a joke. Okay, April the 1st, 8 o'clock in the morning, you guys start the ACT. Okay, some of you will be in my room. Here's my first half of the alphabet, right here. Some of you may be in here, because I typically have the A's, and then maybe a couple B's is what I end up having for my group there. So some of you will be next door, because we usually do the first part of the alphabet here, and then we start working down the hallway, is what we end up doing. And so when we look at that ACT test, why do we standardize scores? Well, I took the ACT. I took it back in '88 is when I took it, almost 40 years ago. We could compare your score to my score. Me as a junior in high school taking the ACT, what did I get? You all, what did you get when you take that score and get it back? We can compare our scores. And that's what we typically think we can do because, hey, it's the ACT. I took it, you took it. We should be able to compare it. The challenge is we can't. Because the way your test is designed right now, structure-wise, content-wise, is not what I was taught, what I was tested on. You guys have what? English? 2 parts. You have grammar and reading, 2 categories of English.
English and reading.
You have English, reading, math, and science, right? Right. We had 1 English, math, science, and social studies. That's what our test was. And somewhere in the mid-90s is when the ACT changed its structure and went to that 2 kind of part of the English with the reading and the English part and dropped the social studies piece.
They're talking about dropping the science piece.
And they're talking about dropping the science piece. So when they do that, it wouldn't be fair to compare just in general the numbers with kids on that test with your test because we're not tested over the exact same type of stuff. So what we do is we standardize it. And that's what we're going to learn today is we're going to learn how do we standardize something so then we can compare apples to apples. All right, because right now, my test score is an orange, your test score is an apple, and we can't compare apples to oranges. But when we standardize it, now I can say who did better. Who has the bigger z-score? And that's what z-scores are used for, is to say, hey, what did better? What did worse? Because once we convert it, now we can compare what that is. Because the converting process makes it what we call standardized. All right, you guys good? I got some of you whispering, so I don't know if I hit a nerve on some of that or not. So a z-score, a value that shows how many standard deviations. We talked about standard deviations yesterday. We had that vocabulary. How many standard deviations a data value is from the mean. Now, the mean is still in the dead center. Again, this is part of our normal curve stuff, so the mean is in the center. When the z-score is positive, the data value is above the mean. It's greater than the mean. When the z-score is negative, the data value is below the mean. It is possible to have a z-score of 0. That data value is the mean. If you have a z-score that is 0, when you do the calculation, that means that score is actually the mean. And again, when we see the formula in a moment, that part's going to kind of make sense. Oh, if I'm getting z for an answer, that means I have to be equal on this one thing so that when I subtract, I get nothing. So what is the formula? Your z-score is equal to, I'm going to use their symbols here, x minus mu over the standard deviation. And again, I usually write this down for my classes. I usually say that in words, the z is equal to the actual minus the mean divided by standard deviation. That's what you're doing more or less as we think about words. Your actual value minus the mean divided by the standard deviation, that gives us our z-score. So what we get to practice here in a few problems is we get to start solving for a z-score in a certain situation based on a certain mean and a certain deviation and also a certain x value, a certain actual score. And then when we do that fraction, that gives us our z-score. Eventually, we're going to spin away from that to where it's going to say, you know what? I'm going to tell you the z-score. I'm going to tell you the mean and the standard deviation. You tell me what the actual score was, which means we're going to do inverse operations and back solve. Because eventually, again, there's 4 variables up there. Z, x, mu, and then standard deviation. Four variables. They're going to tell us any 3. We can find the 4th one. All right, that's what they're going to ask us in different situations. Any one of those variables we can solve for, we just got to know the other 3. So here we have an example here. A radar detector records the speed of a group of cars that pass by. If the mean is 46 and the standard deviation is 2.8, find the z-score associated with each value. So we would go through and say, all right, this is my x, the 52 is my x. So my z-score is 52 minus the mean of 46 divided by the standard deviation, which is 2.8. So 52 minus 46 is 6 divided by 2.8. So now I get to grab my handy-dandy calculator. And there we go. And clear my screen there. And we got 6 divided by 2.8. Tells me it has a z-score for this one is equal to 2.1429. Now, on big ideas, you round to whatever value they want you to round to. I'm giving you some leeway on the big idea stuff on this one. So that's because, again, they're quirky. So now they want us to do the same thing for the 42. Now, again, is 52 bigger than 46? Yes, so should we get a positive answer? Yes, because if you get a positive z-score, that means you're above the mean. And 52 is above 46. All right, so now we're going to do the z-score for 42. So for the z-score for 42, which sometimes they denote like a little subscript, z for 42 is how they write it. We would say 42 minus 46 over 2.8. So 42 minus 46 is a negative 4 divided by 2.8. And so back to my handy-dandy little calculator. Negative 4 divided by 2.8 gives me a whopping total of a z-score of negative 1.4286. So a speed limit of 42 miles an hour is 1.42 standard deviations below the mean. Based on the mean being 46 and a standard deviation of 2.8, having a speed limit of 42 miles an hour lets us know that, hey, you're 1.4 deviations below the mean. Whereas the 52 miles an hour, they were 2.14 deviations above the mean, based on that data. The 47. Now, 47 is really close to 46, so we should get a small decimal here. So a z-score. Sorry, my pen's acting squirrely. A z-score for 47 would be 47 minus 46 over 2.8. That gives me 1 over 2.8. So 1 divided by 2.8. Whoop, that's a 5. 8. There we go. And that tells me that I have a z-score of 0.3571. Now, that should be all fine for when you have to calculate a z-score for big ideas. There shouldn't be any issues. The issue is going to come into play a little bit later on when we have to find certain percentages associated with the z-scores. Sometimes they want to use a table of values. Sometimes they're going to let you use the calculator. That's where the issue is. But that's why I give you a buffer on the homework percentage to get full credit. Just for those little cases there where they get kind of wonky. So next one here. Here real quickly, we change up stages here. They tell us the mean number of total miles ran last week by each member on the track team was 4, so the mean is 4. Standard deviation of 1.2. If Clay's z-score was 2.5. It's not 2.5 miles, it's just his z-score. The answer to that fraction is 2.5 for Clay. How many miles did Clay run? So in this case, they want us to figure out the x value. How many miles Clay ran? So again, with that formula of z is equal to x minus mu over the standard deviation, we're going to change. I say, well, you know what? 2.5 is equal to the actual amount Clay ran minus the mean of 4 divided by the standard deviation of 1.2. Now, should I be getting an answer bigger than 4 or smaller than 4? All right. Those that said bigger, why? When we got done dividing this crud, we got a positive answer. That means I got to have an x value that's bigger than the mean. Because again, positive z-score means the actual score is bigger than the mean. You were above the mean. All right. So again, now it's just an Algebra 1 problem, inverse operations. First thing I got to do, multiply both sides by 1.2. Multiply both sides by 1.2. So I'm going to split my screen. 1.2 times 25. That's yucky math. So with that in mind, 1.2, yeah. Yes, I think I have one more maybe on top of my hard drive. Times 2.5. All right, so there's that one. That's 3. Is it? Yeah, that'll work. And then, well, how do I say? You need a cord for that. Is there one on the hard drive? Yeah, unplug that one right there. Yeah, that one's it kind of blends in with the hard drive and stuff. The whole thing. Okay. All right. So I have now 3 is equal to x minus 4, and then we would add the 4 across, and I find out that x equals 7. So Clay ran 7 miles. That's how many miles Clay ran. Is 7 bigger than 4? So that makes sense. All right? It makes sense. We had a positive z-score. We should get an answer bigger than 7 or bigger than 4, and we did as we solved for it. Again, as we look at these extension problems, we have to be able to solve for any one of those 4 variables. A set test papers is normally distributed with a standard deviation, so fat R is 5. If Riley scored, x is equal to 83, and a z-score is negative, so the z is negative 0.4. So is the 83 above the mean or below the mean? It's below because the answer to that fraction was negative. So a negative z-score means 83 is smaller than the mean. So when I get my math done, I should be getting an answer bigger than 83 is what I should be getting. So again, z equals x minus mu over standard deviation. So negative 0.4 equals 83 minus mu over 5. So the first thing we're going to do is multiply both sides by 5. That gets rid of it there, and I get negative 2 equals 83 minus mu. Bless you. I'm going to subtract the 83 across. Now, this is where you got to be careful when you drop signs. That's a negative 85 equals a negative mu. And then now we divide both sides by a negative 1, and I get mu is equal to positive 85. So the mean for that test was 85. The height of a group of trees is normally distributed with a mean of 14.3 feet. The z-score, if the z-score is 1.9, so that one you had to look at it. The mean is 14.3. 20-foot tall tree, so x is 20 feet. The mean, or the z-score, the z-score is 1.9. What's the standard deviation? So what's the fat R? So z is equal to x minus mu over fat R. So 1.9 equals 20 minus 14.3 over the little fat R. So I'm gonna multiply both sides by that little fat R, the standard deviation, lowercase sigma. Boom, boom. I get 1.9 fat R equals, I'm going to go ahead and subtract those things, and that should give me like 5.7. Now, that's where you got to be careful. I've seen way too many kids will look at that one, and they won't use the calculator, and they'll say 20 minus 14.3 is 6.3. That means somebody forgot to borrow. Okay, so be very careful. If you have a tendency to be a little rusty in your mental math, use the calculator. Okay, because that's enough to make it off. So again, if you're okay with borrowing and keeping track of your place value, decimal place value, is fine in your head. Otherwise, please put it in the calculator. I hate for you to miss something for that silly little mistake, forgetting to borrow and bring it over, and so forth. Okay. So now, when I divide both sides by 1.9, I find out that the standard deviation is 3. 5.7 divided by 1.9 is 3. That's the easy part. Trying to find the z-scores based on information. Again, they got to tell you three of the 4 variables in order for you to use that formula. Okay?
Now, a standard normal distribution. Here's the key thing, standard normal distribution. That means we're using z-scores. That means this normal distribution is based off of z-scores. Just like this little picture here. Instead of us having just random stuff down there that we got to fill in, if they say it's a standard normal distribution, that means all the data values have been standardized. That means that my column headers start in the middle with 0 and they go out by 1 each way, is what that ends up meaning. So in this case here, when you have a standard normal distribution, the mean is always 0. The mean is always, come on, pen. Make me buy another pen. 0. And the standard deviation is 1. Again, I have to remind my stats class about that all the time, about that terminology. Is that when it's standard, that means its mean is 0, standard deviation 1. The distribution is standardized by the z-score. So what that means, in order to create that thing, they took every data value and took the mean, took the standard deviation for the context of that problem, and did that fraction that we just did a couple times up above, and did that for every data value, and then they created this standard normal report, which is a lot of work, okay? Now, with it being standardized, yes, our column headers are nice and pretty. We can actually find the area to the left, to the right, and between two z-scores on a calculator. We can do it on a piece of paper. There's a table. Paige, I think you didn't hand me a stack of stuff that was on your desk. So that's what my first block class, my college stats class, we were doing the table version and also the calculator version. I'm going to show you on this stuff today and stuff in that college stats class. It just happened to line up. We're doing the exact same thing on the same day. So we can use this table thing or the calculator to find the area to the left, to the right, or between values, z-score values, if we want to. Now, here are the directions. Now, I don't teach really how to shade on the calculator because it really has no purpose. But if you ever want to have it shade the graph for you, those are the steps that you use for the shading piece. We usually sketch the shading by hand in my classes, is what we do here. So they want us on this problem here, for an example, and I'm going to walk you through how to do this on the calculator, is they have the golf scores in a tournament is normally distributed, which means I can draw a normal curve. I can use the empirical rule, and we're going to start off that way. It has a mean of 76 and a standard deviation of 2.6. Find the probability. Find the probability that z is less than 2.1. Well, here's the challenge. If we were doing what we did yesterday, and I didn't teach you this new stuff, you would have gone through, labeled the mean as 76. You would start subtracting 2.6. So that would be like 73.4. Subtract it again, and that would be 70.8. And then we subtract it again, and that gives me 68.2. And then on this other side, you would have went through and added, and you would say, okay, let me add to 2.8 and get 78.6. And then I would have gotten 81.2. And then the last one would have gotten us like 83.8, something like that. Okay. Now the challenge is when we look at that statement, it said the probability that z is less than 2.1. Well, first off, is there a 2.1 up on that graph? No. So now we're stuck. All right. Now, what we can do, if we wanted to, they did give us the mean. They gave us the standard deviation. We know technically that 2.1 is a z-score, is what that 2.1 is, because it says z. And so if I wanted to, I could actually convert that z-score to an actual score by doing the fraction we practiced already a couple times. dx minus mu over standard deviation. So we can do that if we, so forth. I'm going to do it once. I'm not going to do it for all the problems. So we could, if we really wanted to use yesterday's thing, we could say, all right, 2.1 is equal to x minus 76 divided by 2.6. And then I'm going to do the math pretty quickly without showing all the steps. I'm going to do it on the calculator. So I'm going to go through quickly here and say 2.1 times 2.6. I get that answer. Then I'm going to add the 76 over. And that gives me 81.46. Now I have a number that's on my empirical rule chart, or at least I can find an area that is. So now I can go through and say, all right, you're really asking me for what's the probability that it is actually less than 81.46. So I go to my chart, and 81.6. Well, 81.6 would be something like maybe about, give me orange, somewhere about here, and less than would be all that area here. So when we think about all those numbers I asked you to memorize, that's almost the whole curve, isn't it? So to me, that's almost like, hey, we're sitting somewhere up there close to 90-something%. Now the challenge is 81.46 is not one of those line markers. I know we're approximately 90%, but that's not good enough. All right, I want to find out exactly. So this is where the calculator can help us out with the process, okay? So what we're going to do, and we're going to go back using the z of 2.1. We're going to go back to using this value here to do the problem. We're going to use a feature in the calculator that's called a normal CDF. A normal CDF. And when we put our stuff in the calculator, you got to put 4 values in there. You got to say a lower bound. You got to have an upper bound number. You got to say what the mean is, and then what the standard deviation is. Those are the 4 things we got to type into this feature. So with this in mind, let's first get the feature up on the calculator. So I'm going to bring up the calculator on the screen. All right, so I got a clear screen. To get to the normal CDF feature, you got to press second vars. Second vars. All right, you got to press this blue button, second, and then the VARS button. And then you'll see it up on the screen. We are using this second one down, normal CDF. Never use the first option. Never. My stats class don't even use it. You got to go to the second one. So we're going to go down to a normal CDF, and we're going to press enter. Now, the first value is my lower bound. Now, here's where we're going to stop and talk about it for a minute. How do I know what my lower bound is? Well, they're asking me in this problem to find the percent that is to the left of 2.1. To the left means everything smaller than 2.1. So the 2.1 is technically my upper bounds. That 2.1 is actually my upper bounds. So the 2.1 would go for the upper 2.1. Sorry, bigger, fatter one there. Now, what is my lower bound? Well, I just got to put in some really small number. Now, 0 doesn't cut it. I have to actually put some really small number there. It's like maybe negative 100. Because if I put 0 in there, 0 is where the mean is. So that means it's going to stop at the mean. I want it to keep going everything less than. I want it to include all the negative z-score percents, is what I want it to do. So my lower bound is a really big negative number. My upper bound happens to be my z-score of 2.1. This is a since we're doing z-scores, my mean is 0, and my standard deviation is 1. So I need to go down here, negative 100, 2.1. My mean is 0, my standard deviation is 1. So that's what you need to have on your calculator. And in a minute, after I press enter a couple times, it's going to tell me what percent is less than 2.1. I know it's a lot. I drew the picture of the graph. I drew this graph, and I know that, hey, 80, 81 point whatever, there's roughly 90% of the data to the left. So I should be getting an answer close to 90% for this thing once I hit enter. Is what I should be getting. So I hit enter, or I hit enter a couple times. I hit enter. I hit enter again. Hit enter one more time. And then now I take a look at it to see, okay, what the heck did Mr. Stevens type in wrong? Oh, I see what I did wrong. What did I forget on the lower bound? Yeah, I forgot the stinking negative sign. Okay? All right, so you saw that but didn't tell me? Is that what it was? You saw it and didn't tell me, Coach, you forgot the negative sign. It's my fat fingers. Negative 100. There we go. All right, hit enter a couple times. That looks a lot better. Remember, just because it gives you an answer doesn't mean you stop and write it down. We got to say, doesn't make sense. All right, so that is what I was thinking, something in the 90 percentile. So there is approximately, again, pen, give me the stuff here. Come on, pen. I have the worst luck with pens. 0.9821. All right, Victor. The syntax error. Let me see if you haven't changed anything, have you? You're using a subtraction sign instead of a negative sign. That's fine. That's how sensitive it is. Okay. And then change that 2.1 to be positive. Yes, Harvey. Do what? Negative? How did I come up with it? You just want... It's a question. Okay. All right, take a peek. Again, if your top lip goes bottom lip. The question was how did I get that negative 100? All right, here's what, it's got to be basically, when I think about the inequality that I am less than 2.1, on my normal curve, the middle is 0. 2.1 deviations is technically somewhere about here. This is where roughly about 2.1 is. And I want everything to the left. If I just put my lower bound is 0, it's not going to add up all this percentage to the left here. So what I have to do is tell the calculator, I want basically on a number line from 2.1 all the way down to negative infinity is what I'm telling there. Now you can put, well, what, can you put negative infinity in the calculator? No. So what we do is we use a really big negative number. All right? So in this case, that's why I'm saying use negative 100. That's big enough in the z-score world to say, hey, I'm telling you to go way down here to the left and never stop. That's when we're using the z-scores. If we were using the actual golf thing, in that case, we can just put like negative 1 million. You know, now can you hit the golf ball negative yardage? I mean, it's possible with a strong wind, but really in reality, no. So in that case, you'd stop at 0. Okay? But again, when we look at my curve that I drew and I labeled it with the numbers, not z-scores, but actual numbers, 0 would have been way out here to the left. And then that kind of makes sense because my curve went all the way out to 60-something to the left. So that's where I came up with the negative 100. It's just a really big negative z-score. All right. Now, could we have stopped at negative 10? Sure. We just don't want to stop at negative 2 or negative 3 because we want to make sure we encompass as much as that curve as we can. And we typically, sorry, that pen went right on it. We typically label out negative 1, negative 2, and negative 3 is what we label out. So as long as we pick a number to the left of negative 3, you know, I would just go negative 10 if you're doing z-scores, or negative 100. I always tell my kids just do negative 1 million. That way you never have to worry about when can I do which one. Just do something really big negative. Yeah. Yes. All right. So, next one. Now, notice on problem number 7, they tell us, oh, instead of using a z-score, like this first one, 6, what's the probability that it's less than 74? So it's not z-scores. Okay. Well, we can use the same feature. We can use the same thing for this problem. All we would do different is we would say normal CDF. And since we're using actual scores, we actually get to use actual numbers. That is still my upper bound. It's my upper bound because I'm less than. I want everything to the left of it. So that means that's my upper bound. If they ever tell me greater than, then that means that number's got to be the lower bound. So right now my lower bound, in this case, technically hitting a golf ball, you can have a swing and a miss. So how far did the ball go? 0. So in this situation, using regular scores, my lower bound can be 0. Since I'm using regular scores. My upper bound is 74. Now here's where I got to make sure I put my mean and standard deviation according to the problem. Mean of 76 and a standard deviation of 2.6. And so now we're going to go to the calculator. Second vars, second option, normal CDF, hit enter. My lower bound is 0, because again, this is now we're not working with z-scores. So my lower bound is 0. I can't hit it negative yardage. My upper bound is 74. And then my mean is 76. Standard deviation is 2.6. And then I hit enter a couple times. And I find out that that is 0.2209. So in the context, there is a 22.09% chance of hitting the golf ball less than 74 yards. That's what that means. Based on my average, my mean for hitting that club, whatever it is, and the standard deviation, what is the probability that I only hit it, or I hit it less than 74 yards? There's a 22% chance that I'm going to hit that ball less than 74 yards. Okay, is what that means. Okay? Now, what's the percent chance for me hitting it over 74 yards? Well, if it's 22% less than, then there's a 78% chance I'm going to hit it greater than 70-something yards, 74 yards, okay? So, because we can always be asked the other way, what's the percent above? Okay? We not always have to do what's below, okay? All right, let's go to the next. Let's go to another one. Oh, here we go. So number 8, back to using Z. Back to using Z. So that means I got to go back to using the mean is 0, standard deviation is 1. Now, they're asking me greater than negative 1.5. Greater than indicates to the right. So that means I'm shading from negative 1.5 all the way out to the right is what that's telling me I'm doing. When I look at my shading, if I drew my picture. I'm starting at negative 1.5 and I'm shading out to the right of my curve. So that tells me this has to be my lower bound. When they're asking you to figure out something greater than, that means that number is your lower bound in that normal CDF feature. So again, to find this probability that Z is greater than negative 1.5, we're going to do a normal CDF. My lower bound is negative 1.5. My upper bound is now something really big, 1,000. My standard deviation, or my mean is 0, my standard deviation is 1. Again, we're back to using z-scores, which means the mean is always 0 and the standard deviation is always 1. Again, I'm doing greater than negative 1.5, so that means that's my lower bound, and I got to do up to something really big. So now as I go to my calculator, normal CDF, my lower bound is negative 1.5, upper bound is something really big. Again, back to 0 and 1 because we're dealing with the letter Z. And so with that in mind, that probability is 0.9332. So 93.32% of the information is to the right or greater than a negative 1.5 deviation. Does that make sense based off of the empirical rule? Well, let me see. Why us teachers memorize useless information. So if I draw my picture of the empirical rule,
There's the mean. There's the middle. 1, 2. There's negative 1.5. And then, now technically from the mean to the right is what percent? 50%. We know this next zone is what percent? 34. Now, we're halfway between -1 and -2, so if that's 13.5 is the whole zone, what's half of 13.5? 6.75. Now I add up those three numbers together. So what is 84 plus 6.75? 90.75. Is that roughly about what I got up there? Yeah, pretty close. It's a, again, the calculator is more exact because it's keeping all the little extra stuff. Okay. Technically this zone is not 34. It's 34.1 something. Okay. So, but that gives me close enough that hey, I should be getting an answer in the 90s or around the 90s. May not be exactly that number, but close. And that's where the empirical rule kind of helps you keep in check what you got out there. Does that make sense? Okay, so to me it makes sense that we should be around that amount because we're saying we are shading all of those zones from this halfway mark over to the right is what that's doing. Okay, so it makes sense to get something around 90 or maybe a little bit above it. It would make sense. Now, number 9, they go back to using a normal x. So this means when I see x, I got to go back to say, okay, my mean is 76. My standard deviation is 2.6. If they use the letter z, we're using mean is 0, standard deviation is 1. If they put the letter x in these little probability statements, I got to use the actual mean and the actual standard deviation from the context of the problem in order in that normal CDF feature. So now, again, same thing. Greater than 81. So I want everything greater than 81. So that means the 81 is my lower bound. So I'm going to do a normal CDF. My lower bound is 81. My upper bound. Now, this is why we do big numbers. I can hit the golf ball 100 yards. I can hit the golf ball 310 yards. So when we're talking about doing actual yardage, I need to make sure I'm 1,000 yards, I'm 10,000 yards, because can you really hit the ball 1,000 yards? No, nobody can. Okay? I think the longest drive somebody can hit, like where they do the long drive contest, is somewhere in the 500s. So that's why, hey, 1,000 is fine for using as an upper bound. If you want to use 10,000, you want to use 1,000,000, that's fine. We know theoretically you can't hit it unless you're Superman or you're on the moon. There's no gravity to stop the ball from going. Okay, so we just don't want to stop at 100 in this case because 100 you can hit 100 yards. Okay, we need to make sure we're counting all the other stuff. So as I go through there, my mean again, we have to use the actual. So the mean, come on. There we go. Mean is equal to 76. And then the standard deviation is 2.6. I really don't want to have to sneak another iPen or another pen on my wife's Amazon account without her knowing and stuff. So it's just payback for all the times I paid for stuff I didn't know I was paying for and stuff. So I love my wife. She puts up with me. All right, so my lower bound is 81. My upper bound is 1,000, 76, and then 2.6. And so the probability that I hit it more than in this case, greater than 81. All right, greater than 81 is 0.0272. So there's a 2.72% chance that I hit it more than 81 yards. Okay? Based on the data, based on the mean being 76 with a standard deviation of 2.6, there's only a 2% chance. Almost 3% chance of that happening. Now, does that make sense for the empirical rule? As I think about it? All right, so, with that in mind, I don't have my picture there, but didn't I draw, like, as I did it, wasn't that number there like 81 points, like 3 or 2? Something like that, I think it was with that. No, that was the second one. This Something, because it was 76 plus 5.2, so that's 81.2 is the second one. So 81 is technically just a smidge right in front of there. And so what are these last two zones? These last two zones are 2.5 just in general together. 2.35, 0.15, and I'm just a smidge to the left of that line. That's where that extra, that's where that extra, 2 thousandths come into play. Instead of being 0.025, it's like 0.027. That's where that extra 2 thousandths, because I'm a little bit to the left of that line. Okay, so yeah, that makes sense to me. I should get something small. Now, the beauty about these, and since we already have the standard, we have the 76 and 2.6 in there, the great thing about this the calculator feature here is when they ask me for the between stuff. The smaller number is the lower bound. The bigger number is the upper.
Mr. Stevens?
Yes, ma'am.
Hi, can I have Giselle Guerrero for early difficulty in cover?
Of course you can. Yes.
Thank you.
Yep. So as I do this problem, we're going to do a normal CDF. My lower bound is 77. My upper bound is 83. My mean is 76. And my standard deviation is 2.6. And so I did this one first just because we had those other numbers stored in there. So second vars, normal CDF. All I got to adjust is the lower and the upper bounds. Arrow down to the bottom. Hit enter a couple times. And boom. So 0.3467. There's a 34.67% chance or probability of hitting it between 77 and 83 yards. All right. Now, on the problem at the top, did it say what club we were using? No. How many of you have ever golfed before? Okay. So there's more than one club. All right. So probably when I think about what is this data in context, it's probably somebody's pitching iron. Their sand wedge or something like that. Something they're going to use when they're close to the green. And so therefore, when I was playing golf the most in my life, when I was younger, I could hit my pitching wedge 100 yards consistently. Okay, is what I could hit. Now it's sporadic. Sometimes I hit it 100, sometimes I hit it 80. Because I haven't played, I had about a 12-year gap between playing golf. All right, I played more golf this last year as being a golf coach than I had played in probably the past decade and a half and stuff. I still shoot somewhere in the 90s for being off of golf for about 10, 15 years. Sometimes I shoot above 90 to 100 when I get really sporadic and stuff. But when I'm honed in and I concentrate and I don't try to kill it, I shoot pretty darn good and stuff. But that's the challenge about golf. It's a mental game. You're like, hey, I got a good shot here. There's times with my sons and sons-in-law, we would go out golfing on a Sunday morning, and I get up there and they're younger, of course, they're 30 years younger than I am, and they get up there with their driver and they hit it like 270, 280. I get up there with my 3-wood, which is not supposed to go as far, and I hit it 300 some yards. And they're like, what the heck did you do? I said, well, my timing was just right. I had everything lined up. I didn't pull my head, I didn't pull my shoulder, I didn't dip my back arm, and I used dad strength. Straight through and stuff. Next hole, went 100 yards on the front and stuff. It just happens. Sometimes they're good, sometimes it's bad. So to me, that to the context of this one is like somebody's driver, because that's what we always talk about there, or pitching with. We say, hey, how far away from my golf tee? How far away from the hole? All right, we're this far. What club do you hit consisting around that amount? Do you need to club up or club down? And stuff is what we go through and we talk about.
Well, I consistently hit this club about this many yards. Okay, then that's the club you want to hit. Okay? And then that's when we talk about the strategy in situations. We also keep in mind like what is the wind doing? If the wind is blowing hard, we're like, okay, maybe we want to go to a different club because we don't want it to go up in the air so the wind catches it and affects it. So let's take a peek to see if we need anything else here. I think we're pretty good. So the empirical rule, as you saw me do the empirical rule, that's what we did yesterday. The empirical rule gives us a nice approximation of what percent is to the left or to the right or between things. So nice rough approximation. Using this feature, using z-scores, or using the actual stuff, remember we're adjusting the mean and the standard deviation with this calculated feature, it gives us a more exact percentage, is what it gives us. So when we're really trying to make decisions, because that's what statistics is, it's making decisions about the data, I want the most exact answer that I can get before I make that decision. So using this formula of the feature in the calculator, there's applets on the internet that do the same stuff. Using that to get the most accurate picture helps me when I'm trying to make big decisions. If I just want a rough approximation, that's where the empirical rule comes into play. So when you look at our test on Thursday, and I'll reiterate this tomorrow, I'm going to be super, super nice on this one, because the EOC, they're not nice. Okay, they don't give you a heads up. But I'm going to put on the problem empirical rule, and if I don't put on the problem empirical rule, that means you're using the calculator feature. Okay, so I'm going to indicate which ones I want you to use, the 34s, the 13.5s, and that zone stuff. Okay, I will let you know for this one. End of course exam, they don't tell us. You got to read the problem. Now, what's a giveaway is when you look at the percents for answers for an multiple choice. If you start seeing 34, 68, 95, nice whole numbers like that, you know that they're using the empirical rule, 2.5. If I start seeing crazy decimal things like 92.33, I know they're using the calculator to get that answer. That's how we know on the state test. How do I know which one do they want me to use? If it's a nice number like that, that's why I say memorize the chart and stuff, the zones. Because if you see those numbers, they want you to use the empirical rule. If you don't see those numbers and you see whacked out crazy decimals, that means we use the calculator feature. That's how we know which one to do. On Thursday's test, I'm going to break down the empirical rule on the problem. And that way you know to use that one. If it doesn't say it, then I want you to use the calculator feature. Just pay attention if it's a Z or an X. If it's a Z in the parentheses, that means you're using a mean of 0, standard deviation of 1. If it says X in the parentheses, you're using the actual mean and the actual standard deviation for that board problem. Is what you're using in that feature of the calculator. Okay? Questions? Okay. What is who? What? Number 10, 55.
Can you try it and then you
What is it, negative? What'd you say, sweetheart?
I was going to say, wait.
I'm going to do number 10 here for a second. Kaden asked me to do number 10, so I'll do number 10 on the video. All right. So I'll do number 10. Now, you want me to be a smarty pants and tell you what it is, what I think before I actually do it? So negative 0.2 to the side there is about maybe 15%, 49%, and then almost that next section there. I'm going to say our answer is going to be pretty darn close to 60%. That's what I'm thinking. So here we're going to do, when I look at my normal CDF, my lower bound is negative 0.2. My upper bound is 1.8. My mean, again, they use the letter Z, so my mean is 0. My standard deviation is 1. And then we're going to see how close my rough estimate of around 60% is. So second VARS, normal CDF. My lower bound is negative 0.2. My upper bound is 1.8. Go back to being a mean of 0 and a standard deviation of 1. Hit enter a few times. Oh, I was pretty good. 54%. I would have really shocked you because I was thinking about 55 is what I was thinking. I mean, I would have really like blown your all's brains if I came up with that. Just like quick estimation. You what?
So you said 55.
No, I did say that, didn't I? So, So, again, big thing here, and this is why it helps to write the stuff down. When you see the Z, you want the mean and the standard deviation to be 0, 1. When you see the X, you want to write the actual stuff. And that's where, I know it's a really easy calculator activity, now that you know how you can plug it in. But you need to practice writing it down so you know when am I switching those to zeros and ones, when do I need them to be the actual one from the problem, okay? So I'm going to turn off the video, I'm going to turn you loose. I don't think the homework's out there, but I'll go in there and release it so that it's out there.